So a monochromatic light beam of frequency 6.0 hertz crosses into a transparent material where its wavelength is measured to be 300 nanometers. So the frequency of the light the 6.0 times 10 to the power negative or positive 14 hertz. Then wavelength lambda. Wavelength, the way some of you were designing this symbol, it leaves much to be desired. Hey, the wavelength 300 nanometer. What is the index of refraction of the material? So the refractive index of the material. Okay, here we earlier learned about absolute refractive index. An absolute refractive index N or mu can be C over V. This is also equal to lambda in air over lambda in a medium. So it means that we can use these two possibilities to find the absolute refractive index. Okay, when we do the first one, it means if you want to use N is equal to CV, then we must know the speed of the light in the medium. As for speed of light in air and vacuum, it is a constant value, 3 times 10 to the power 8 meter per second. Okay, so we need to know the velocity of light in the medium. How do we do it? Velocity of a wave relates to frequency as f lambda. So for a wave, the velocity or speed of light is given as the product of the frequency and the wavelength. Now, please note this, whenever light moves from one medium to another, speed and the materials have different optical densities, velocity and wavelength changes. When light moves from one medium into another medium, its speed or velocity and the wavelength changes. In fact, wavelength V is the velocity of light or wave is directly proportional to the wavelength. Now, proportionality, when we introduce an equal to sign, we have a constant of proportionality times the wavelength. This constant K of proportionality, K is equal to the frequency. The reason for which we say that V is equal to F lambda. F is a constant. This is equal to a constant. Meaning that it's a constant, it doesn't change from one medium into other medium. So whenever light travels from one medium to another medium, its speed changes. Once it changes, wavelength would also change. But its frequency is always constant from one medium to another medium. Okay, so we are told that the light has a frequency of 6.0 times 10 to the power 14. It means that this frequency of light is the same from air into the medium because frequency is constant, does not change. Class, please, is that okay? So you must understand that. All right. So if we want to use the first relation to find the um the refractive index, then velocity of light in a medium is given by the frequency times the wavelength. Okay. And here we are talking about wavelength of light in the medium. So let's go back to the question. A monochromatic light beam of frequency passes from air into a transparent medium, where its wavelength is measured to be. So the 300 nanometer is the wavelength of light in the medium. Therefore, the velocity would be equal to the frequency times wavelength 300 times 10 to the power -9. Nano is -9. Okay. So multiplying frequency by wavelength gives us the velocity of light in the medium. So we have 1800 times 10 to the power -5. Sorry, 45 meters per second. This becomes the velocity of light in the medium. Therefore, using n is equal to c over v, we have 3 times 10 to the power 8 divided by 1800 times 10 to the power 5. Now we can express the denominator in terms of
It's a lot for you to this thing fast travel.
alpha. Leonard, mute yourself. So 18 times 10 to the power. Okay. 1, 1, 2, 3, 1.8 times 10 to the power 8. So that this and this cancel. We have the refractive index being equal to 3 on 1.8. And I think this is 1.667, approximately 1.67. Okay, so if you want to use refractive index equal to speed of light in air over speed of light in a medium, that's it. Now, if you want to use this one, refractive index equal to speed of light in wavelength in air over wavelength in a medium. We have wavelength of light in a medium, which is 300. We need to know the wavelength of light in the air. Now, using speed of light in air equal to frequency of light times the wavelength in air. C is a constant, F we know. Frequency of light does not change from one medium into another. So this is constant. Therefore, lambda in air is equal to C over F. And we have 3 times 10 to the power 8 over 6 times 10 to the power 14. And this is giving us is equal to 3 on 6 is half times 8 minus 14 or 14 minus 8. This is -6 minus 6. So if we change this to decimal, 0.5 times 10 to the power -6. Maybe I want to express this in nano so that it will look beautiful, meaning I have to shift the decimal point 3 times. 1, 2, 3. And so I'll have 500 times 10 to the power -9, giving us 500 nanometers. Now, if the wavelength of light in air is 500 nanometers, Let us bring it here to calculate for the refractive index. Therefore, refractive index equal to lambda in air over lambda in a medium. We have 500 times 10 to the power negative 9 divided by wavelength in a medium, 300. 300 times 10 to the power negative 9. That's a difference of 3. That was cancel 5 divided by 3. What is 5 divided by 3? Audrey.
Sir, please, I've gotten lost at where you found the frequency of air.
So I was over
Sir,
here.
please. No, sir, at the last point there. I
You
was
mean
thrown off.
this part?
Yes, sir.
We're looking for wavelength of light in air. Okay, and we are using the relation V is equal to F lambda. Now we change V to C because we are talking about speed of light in air, which is constant. And this is represented by the letter C, the reason for which I change V to C. So C is equal to F times wavelength of light in air. C is known, constant, 3 times 10 to the power 8. F, frequency of light does not change from one medium to another. So when you make lambda in air the subject, this is what you have, 500 nanometer as a wavelength of light in air.
No, sir, I meant like when you got 0.5 times 10 to the power negative 6. I didn't get how it became 500 times 10 to the power negative 9.
Okay, I get you. I was just trying to express that in standard form. I have 0.5 times 10 to the power negative 6. But I want to express this as nano. Nano is 10 to the power negative 9. And so it is like moving this decimal point 3 times because I only need negative 3 to add to this to give me negative 9. So I'm moving it 3 times. 1, 2, 3. Just to express it in nano. So when you move it 3, you have 500 times 10 to the power negative 3. Okay. Times the already existing 10 to the power negative 6. So this will add up to give me 500 times 10 to the power negative 9 meter. And this is what we are calling as 500 nanometer. Are you okay?
Yes,
Audrey,
sir.
are you okay? So I was just
Put your hand there.
I did.
I was just doing to make it look like the orange figures that we have. Okay.
Yes, sir. Thank you, sir.
So we have 5 divided by 3. And what is 5 divided by 3?
Hey, Jovuna.
1.67.
So 1.67, approximately 1. So this is also giving us the same results as when we considered speed of light in air to speed of light in a medium. So both ways, okay, are all applicable or desirable in solving the problem. Please, any questions? Any
No, please.
questions? All right. Yes, sir. I think one of you sent me a very interesting something which I need to share with the class because it's an application of some of the things we have done and it's worthy to be looked at. Relative refractive index, as we compare the refractive index of one material to the refractive index of another material. In fact, when we talk about refractive index of material, we are actually talking about the absolute, which is the real refractive index of a material. Okay. All other indices, fine, will be specified. Reverse refractive index, relative refractive index. But when we talk about refractive index, we mean the absolute refractive index or real refractive index of a material. So we define, or we saw that whenever light moves from one medium into another, maybe from air to glass, refractive index, absolute refractive index of glass is mu. Let me use your favorite N. A. Absolute refractive index of glass, mu G. Is a substrate, please. So when light, okay, I'm talking about relative terms. So let me change this to maybe water. Meaning we are comparing the absolute refractive index of water to glass. So the light is incidented in water, angle of incidence, since glass is denser than water, it will bend towards the normal, and this is R. So we saw that for a composite media, two materials that are joined or joined together, the product of the refractive index of one, the first one, and the sine of the angle of incidence must be equal to the product of the refractive index of the second one and the sine of the angle of refraction. So we made sine I over sine R the subject, and then got refractive index of glass, refractive index of water. And since this is Snell's law, and this is the refractive index as light moves from water to glass. So the refractive index as light moves from water to glass or glass with respect to water is equal to the absolute refractive index of glass divided by the absolute refractive index of water. And this is what we saw to be relative refractive index. So whenever you have two medium and the light comes from the refractive index of the first one, N1, N2, light is from first one to the second one on condition that the second one is denser than the first one, then the absolute refractive index mu 1, 2 will be equal to mu 2 over mu 1. This can also be expressed in terms of speed of light. You know, absolute refractive index of glass, absolute refractive index of glass, mu of glass is equal to speed of light in air divided by speed of light in glass. Then absolute refractive index of water can also be speed of light in air divided by speed of light in water. So when you substitute this here, you have C over VG divided by, so times VW over C. This and this will cancel so that we have VW over VG. Okay. And this is VW is the speed of light in water divided by the speed of light in glass. So relative refractive index can also be expressed as speed of light, okay, in the first medium to the speed of light in the second medium. Class, please, is that okay?
Yes, please.
All right. Then we learned about reverse refractive index. Reverse refractive index. For reverse refractive index, light was considered as moving from air into one material. So water or air, first medium, air to water. I R. Audrey,
Sir, please, your line is breaking.
class, is it a general problem to all?
Yes, please.
No, please. No, please.
Oop, God.
If Audrey, if it is recurring, you can you can move and then come back again, right? Just reconnect for me if that problem will be fixed. So light is from air to water. When you apply Snell's law, the refractive index as light moves from air to water is equal to sine I over sine R. When you reverse this, when you take the part of light to be moving from water, refractive index as light moves from water to air, you have the refractive index being equal to sine R over sine I. You see, the difference between these two is that this is absolute refractive index, and this value is reverse refractive index. I told you that absolute refractive index of a material is always greater than 1. This is because the numerator is always greater than the denominator. Reverse refractive index is less than 1 because it's the other way around. Okay. Then the concept we developed was that the product of the absolute refractive index of a material A to W. Please, if you have a question, ask. Times refractive index from water to air. This product is always equal to 1. So for two composite material, when you take the absolute refractive index and then you take the reverse refractive index, the product of these two must always give you 1. So sometimes questions can be tricky. The reverse of refractive index of a material can be given to you and you may be asked to calculate for its absolute refractive index. Okay, or the other way around. It is this situation that this is given for you to find the absolute refractive index. Then absolute refractive index would always be 1 over its reverse refractive index. Take note of this. The second relation is just coming out of the first one. Okay. The product of the refractive index of a material and its reverse refractive index is always equal to 1. So if the materials are not air and water, maybe they are labeled as 1 and 2. 1 and 2, medium 1, medium 2. Then I can say that the refractive index from 1 to 2 times the refractive index from 2 to 1, this product is equal to 1. Very, very important. And we are applying this as we go on in physics. Please, any question? So this is for composite, 2 composite material. Let's look at 3 composite material. 3. When you have 3 different materials that are joined together, so I have 3. The first one, this is air. The second material is water. The third material is glass. So the light that enters glass, air, water, glass, and then comes out through air. The refractive index of air, mu air, either mu or A, please take note. Refractive index of water, mu W. Audrey, explain better now.
Sir, please.
A little bit.
Sir, please, I did not hear you.
I'm asking if your line is better. You are complaining of breakage in my communication.
Sir, please, it's better now.
Okay. So this is the normal. Please note that refraction of light occurs at the boundary between the two media. So the horizontal line represents the boundary separating the two media. When light is incidented through air, when it gets to the boundary between air and water, it will deviate, and the deviation is such that it deviates towards the normal. This is angle of incidence I. This is angle of refraction R. So long as the light is propagated through water, it will not deviate. The moment is about entering into glass. Deviation. Okay, that's why I said refraction occurs at the boundary. So this is a second normal, N2, N1. From water to glass, light bends towards the normal, the more R reduces. Let me increase it a little bit. So this angle of refraction, of course, will be different from this. So let's call this R, and this is R1. Once the light is coming out through air, enters air and comes out through air, it will deviate away from the normal. We call this angle of emergence, where the ray is emerging out of the material. So we are going to, as I said, refraction or deviation of light occurs at the boundary. Please, let me take a quick shot of attendance, okay? A quick shot of attendance and drop it in the group. So, as I said, refraction occurs at the boundaries. This is boundary 1, boundary 2, and then the third boundary. If we apply or derive Snell's law, a sense of refraction here, then refractive index as light moves from air to water will be equal to sine of I over sine of the angle of refraction R. This angle of refraction is represented as R. This is for boundary 1. For 1. Then for 2, boundary 2, the extent of refraction by Snell's law, refractive index as light moves from water to glass. Water to glass. G will be equal to, now look at this, because this is the same medium water, the angle of refraction here will be the same as the angle of incidence here. They alternate. But as the theory said, deviation of light or light does not deviate when it moves through a homogeneous medium, one medium. So the angle of incident refraction here will be equal to the angle of incidence there. So sine R over sine of, because this is water to glass, the angle of refraction will change from this. So this is R1, R subscript 1, just to create that distinction between the R here and then the angle of refraction here. Please, are you with me, class? So this is for the second boundary. Now, finally, the extent of deviation at the third boundary. So this is the refraction index as light moves from glass to air. Glass to air. And this will also be equal to, because this is also the same medium, glass, this will alternate with this. So we have sine of R1 over sine of E. So this becomes the deviation or refractive indices at each of the boundaries. Now look at these boundaries. This boundary is parallel to this, and it's also parallel to this. For refraction of light at parallel boundaries, for refraction of light refraction of light at parallel boundaries angle of incidence is equal to the angle of emergence. All that we are saying is that because these three boundaries, this one, and this one are parallel, at the end of it, we expect angle of incidence I to be equal to angle of emergence E. Hello, class, are you with me? Give me feedback. Are you clear?
Please, can you come again?
So we derived refractions at each of these three boundaries. For air to water, refractive index of air with respect to, refractive index of water with respect to air. That with respect to, please, refractive indices can be expressed in different ways. This can be refractive index of water through air or with respect to air. Here we are referring to water, but through which medium? Or refractive index from air to water. So either we describe it as refractive index of the second one through the first one, or with respect to the first one, or refractive index from air to water. So air to water, or water with respect to air, is a sine I over sine R. Then glass with respect to water, or from water to glass, the refractive index is sine R over sine R1. Then refractive index of air with respect to glass, this is reversed, or from glass to air, this is equal to sine R1 over sine E. Now, for the fact that the boundaries separating these three materials are parallel, we expect the angle of incidence I to be equal to the angle of emergence E. If this is the case, then let's determine the products of all the refractive indices at the boundary and see what will happen. That is the concept we are actually testing. So refractive index from air to water times refractive index from water to glass times the refractive index from glass to air. We are looking for the product of all the refractive indices. This becomes sine I over sine R times sine R over sine R1 times sine R1 over sine E. Sine R cancels R. Sine R1 cancels sine R1 up there. We have sine I over sine E. We just saw that for refraction at parallel planes or boundary, I is equal to E. or E is equal to I. So we can change E to I, and this is equal to, the result is equal to 1. Okay. So for 3 composites, Audrey,
Sir, please, I didn't catch the last part.
the last part, you see, this is what we had when we cancelled that sign I over sign E. But Audrey, when you mute yourself, the concept we developed was that refraction at parallel boundaries I is equal to E for refraction of light at parallel boundaries. So if I is equal to E, then it means that I and E are equal. And so this can also cancel out so that the result is equal to 1. So when you have 3 materials or media joined together, the product of their refractive indices in that orderly manner. But this works, the product of their refractive index in that orderly manner is equal to 1. But it works on the condition that here we have increasing refractive indices. Mu air, there's a condition, mu of air is less than mu of water and it's less than mu of glass. So this is the condition. It's the refractive indices must be in a certain order, either decreasing refractive indices or increasing, meaning that when you mix it, it will not work. The rule will not work. So for composite media or material that are joined in order of increasing refractive indices or decreasing refractive indices, the product of their refractive indices, mu from air to water times mu from water to glass times mu from glass to air, the product must be equal to 1. There are 4, and it follows that order, the same thing, 5, on and on. Is that please? Is that okay?
Yes, sir.
So it can be, let's label the materials with numbers, maybe 1, 2, 3, but it should follow a certain order. This is material 1, material 2, material 3. This is the same as the 1. But don't forget the order must be that mu refractive index of 1 must be less than refractive index of 2, must also be less than refractive index of 3. Or it can be, or mu of 3 must be greater than mu of 2, greater than mu of 1. Meaning, if you don't follow the order and you miss it, the rule or the formula wouldn't or happen. So if it's the case, then the refractive index of 1 to 2 times refractive index of 2 to 3 times the refractive index of 3 to 1. The product must be equal to 1.
I know one of friends.
KJC, KJC,
Snap.
KJC, we can snap.
Jimmy, go snap.
Let me mute KJC before he says everything. Okay, a question. A question to the class. The refractive index of glass with respect to water. The refractive index of glass with respect to water is 9/8. is 9/8. Refractive index of glass with respect to air, refractive index of glass with respect to air is 3/2. Find the refractive index of water with respect to air. I take the question again. The refractive index of glass with respect to water is 9/8. Refractive index of glass with respect to air is 3/2. Find the refractive index of water with respect to air. So, some minutes just to try, please. 5 minutes to attempt.
Please, can you take the question again?
I'm
I'm
coming.
coming in.
The
The
question
question
says
says
that
that
I'm
I'm
coming.
coming.
The refractive index of glass with respect to water is 9/8. Refractive index of glass with respect to air is 3/2. Find the refractive index of water with respect to air. So you have to calculate for the refractive index of water with respect to air. So water with respect to air. But what are you given? You are told that refractive index of glass with respect to water is 9/8. So glass with respect to water is 9/8. Refractive index of glass with respect to air glass with respect to air is 3/2. Find the refractive index of water with respect to air. So
Please,
think
can I
through
see
it
the
for
bottom of the screen? The board, sorry.
you. Are we true? It's supposed to be an easy one, oh, so okay. I'm sure you are true. Let's go through the question. Okay. Angel, Angel, Angel is not here. Audrey, Audrey is also
Yes,
gone.
sir.
What
No,
did you
sir, I'm here. Oh.
what did you get as your final answer?
Sir, please. I had 16/27.
16/27.
Yes, sir.
So we have 16/27 as one of the more views. Leonard, what did you also make? Erefua, what's your answer? Okay, Mamiya. Mamiya, what did you get? Mamiya, Frida,
Say,
what did you get?
yes, I had 16/27.
Okay, same as what Odrick had. Leslie, share with us what you also got.
Yes, I have 4 and 3.
Speak up.
4 divided by 4 and 3.
4 and 3. Okay, so we have 3, 2 same, and then 1 different. Let's see who is who. So the refractive index of glass with respect to water is, so glass with respect to water. I just want us to understand this. What it means is that with respect to means to water. So this becomes either mu from water to glass. Okay. Or the symbol can also be mu from water to glass. Whichever one you are comfortable with. That's I think. So that's the meaning of the with respect to. So if the refractive index of this and that values are given, we know that for air it's about 3 materials: air, water, and glass. If refractive index of air must be less than refractive index of water, must also be less than refractive index of glass, then we can say that, oh, okay, then refractive index from air to water times the refractive index from water to glass times the refractive index. I'm missing the symbols. Glass to air, this product must be equal to 1. So the big question is, do we have the refractive index from air to water? This is what we have to calculate for. Do we have the refractive index from water to glass? Yes, that is 9/8. So mu to water times 9/8 times. Do we have the refractive index from glass to air? What we have here is air to glass and not glass to air. But there's one thing that we know, and that is for if you have Na2, the refractive index from air to glass times its reverse refractive index, glass to air. This product must be equal to 1 by Na2. So if we are given from air to glass, then we can find from glass to air using this equation. So 3/2 times refractive index from glass to air is equal to 1. Therefore, the refractive index from glass to air is equal to 2/3. It is actually 1/3/2, which is equal to 2/3. So using the absolute and then the reverse, we could get the unknown. Then we substitute it into the equation. So we found it. So 2 to 3 must be equal to 1. Okay. 2 goes into 8, 4. 3 goes into 9, 3. So we have mu from air to water B times 3/4 is equal to 1. Therefore, the unknown air to water is equal to 4/3. So the answer must be 4/3 as said by, let's see. Any question? If you have any question, if you don't have any question, I give you another trial. Okay, another question. Another question. Given that the refractive index from 1 to 2, from 1 to 2 is equal to 3/4. From 1 to 2 is equal to, given that the refractive index from 1 to 2 is equal to 4/3. Sorry, 4/3 rather. Mu 1 to 2. Mu 1 to 2 is 4/3. And the refractive index from 2 to 3, mu from 2 to 3 is equal to 3/2. Find the refractive index from 1 to 3. find the refraction index from 1 to 3. So this is the question. Finish. Yes. Give me your answers. What have you had? Elizabeth,
Yes, please.
what have you had?
Please, I had
Elizabeth, your line is breaking.
please, I had
You had 2.
yes, please.
Gabby, what have you had?
Is there some final touches on my done?
Julian,
Yes, sir.
Julian, what have you had? Or you are not done?
No, sir.
Nanajua,
Yes, sir.
what's your answer?
2.
2.
Yes, please.
Rashid, share with us what you have. Okay, so let's look at it. Audric, what did you get this time around? Audric. Okay, let me go to Leslie. Leslie, share with us what you had.
Please, I had 1/2.
1/2. Let's see. So the other is that mu, if mu of 1 is less than mu of 2 and it's less than mu of 3, then we can say that refractive index from 1 to 2 times refractive index from 2 to 3 times refractive index from 3 back to 1. The product must give us 1 or must be equal to 1. Whose mic is not working? Okay. So if we have this, then this is what must happen. We have from 1 to 2, yes, 4 on 3. Do we have from 2 to 3? Yes, 3 on 2. We have to calculate for 1 to 3. But we can, out of this, we can find 3 to 1. So this and this goes into this. So 2 times mu is equal to 1. Refractive index from 3 to 1 is equal to 1 over 2. But this is what we can ask to find from 1 to 3 or 3 with respect to 1. So we know that mu from 1 to 3 times mu from 3 to 1, this product must be equal to 1. So if 3 to 1 is half, then 1 to 3 will be equal to 2. Mu from 1 to 3 will be equal to 2 or 2 over 1. So those of you who answered 2, you are right. Okay. Those of you who got it wrong too, better luck next time. All right. Let's look at real death and apparent death. Real death, I wish today we can quickly even go through total internal reflection. So before that, let's look at real death and apparent death. Whenever you drop pen or pencil in a water, okay, water in a car or building, you see the outer end, that is the boundary between air and water, as if the pencil or the stick is bent. That is apparent view, optical illusion, where you drop a coin, or when you look at fish in an aquarium or pond, the fish always looks closer than it actually is. Apparent optical illusion. So that concept is what we are going to look at. The concept of optical illusion. So real death and apparent death. and how to use this concept to calculate for refractive index of the liquid. Okay, so I'm going to create a situation where water in a cup. Or water in a bowl or basin. So this is water in a cup. An object such as a stone is placed under. An observer stands. Okay, so whenever light, you see, we see as a result of reflection or refraction. So before you see an object, light has come from the object. Now, when the light coming from the object is such that it is going light from the spot of the object, light from this part of the object coming out of the water. Now, because it is water air boundary, we draw a normal. So N1, N2. These are rays coming out from the water, from the object. It's from the object. Now, because the ray is coming out of water to air, when it gets into air, it deviates away from the boundary or from the normal. This will also do same because it is a ray is coming from water to air. At the boundary, it will deviate away from the normal. So let's extend the refracted ray. When you extend the refracted ray, where they intersect becomes the apparent position of the. So this is where the two extended refracted rays are meeting. Meaning that if you are an observer watching this from up here, this is where you see this image formed. So when a fish is in water and you are looking at the fish from air, the observer sees the fish as if it is here. Okay, the distance from the top to where the object is the real depth. This height is a real depth. That is height. Then the distance from the top to where the image of this object within the water is the this distance is the apparent depth. So that's the concept of real depth and apparent depth. An observer up here would see this object lying under the or within the water as if it is here, very, very close. And that is what we see whenever we are looking at fishes in water or in rivers or in an aquarium. This is what happens when a glass prism or glass block is placed on coin and it is viewed from above. When water is put in a basin and all that, and sometimes there's magnification. You also see the object as if it is so magnified. So this is the concept of real depth and apparent depth. Please,
You
any
never
question?
take this to the next level.
Any question? Okay. Now let's go into calculation of refractive indices using real depth and apparent depth. So the same diagram, but this time around we'll look at it from one side. A basin or a basin of water. Let me draw it this way rather. So an object is here. A ray of light coming perpendicularly or directly from the object goes undeviated. So this is a ray which is hitting the surface of the water at 90. It goes undeviated. Then a ray of light hitting coming from it at an angle. Let's draw the normal. Because the ray is from water to air, it deviates away from the normal. So the refracted ray moves away from the normal. When we extend this, the refracted ray, this is where it meets this refracted ray. So this part becomes the apparent position of the apparent image, just as this one, real depth. So the object itself and then the image, object image. Here, the observer is looking at it from one side. So this is the eye of the observer. Over here, the observer is looking at it from the top. Now, this is the angle of incidence, I. That's the refracted ray. So this becomes the angle of refraction R. the angle of refraction R. This angle is equal to this angle because they correspond. So if this is R, this is also R. Please open your eyes very well and watch. We are going to derive a relation. So let's represent this with letters. This point is A, where the object is A. This is B. This is C. And this is D. We have two right-angled angles over here. We have triangle. This is perpendicular to this. The smaller one, B, C, D. B, C, D. And we have triangle A, C, D. Class, are you following?
Yes.
Yes.
So we have these two triangles. Now, I want us to consider, take the sine and cosine of what we have in there. If we take the sine of I, sine I over here, help me derive an expression for sine I. I has to do with triangle A, C, D. Help me find sine I. Anybody, sine I. Using triangle ACD. Oh, let's see. Sine I, sine of I. Using triangle ACD. Sine I.
1.
Hey, of you is contributing. Help me derive sine of I using triangle ACD. The bigger triangle. Elizabeth.
Please, AC over A.
Sine I. Don't forget sine is opposite over hypotenuse. So look at it again. Triangle triangle ACD. Yes. Elizabeth, come again.
It's a AC over A.
No, sine is opposite. Opposite CD over the hypotenuse AD. Right? So sine I is equal to CD over AD. CD over AD. Help me find tan I using the same triangle. Tan I, Elizabeth. Tan I.
Please, CD over AC.
Tan is opposite. So CD over AC. Thank you. So CD over AC. Then I want you to help me find sine R. Sine R. R this time has to do with triangle BCD. You'll find sine R in triangle BCD. So Elizabeth, sine R.
CD over B.
B.
CD over BD, sorry.
Thank you. So CD over DD. DD. Then tan of R. What about tan R?
Please CD over BC.
CD over BC.
Yes, please.
CD over BC. Okay. Let's find the refractive index of what we are doing. But it's now so when light is moving from one medium into another medium, Snell is saying that the refractive index, this is from water to air. The light is moving from water and coming out of air. So Snell is saying that it is equal to sine of the angle of incidence I over the sine of the angle of refraction R. Gabby and Co, are you following? The guys, are you following?
Yes, sir.
Yes,
Okay. Now, you see, the condition for this is that we consider small angles, and this is termed as normal incidence. Normal incidence. Normal incidence here means that we are considering small angle of incidence I and will give us a corresponding small angle of refraction R at normal incidence, meaning I is very small. And if I is small, I will also be small. So when you consider at normal incidence, sine of I is just equal to tan of I, and sine of R would also be equal to tan of R. We are equating them because at very small angles, sine I would just be equal to tan I, and sine R would also be equal to tan R. So instead of equating sine I from what you've done, we would rather pick tan I and tan R because that will help us get the expression we are looking for. When you look at what we've done, tan I is equal to CD over AC. Then sine R is also equal to tan R, and tan R here is equal to, so over CD over BC. Mathematically, CD over AC times BC over CD. You have this and this canceling out. Okay, so the refractive index as light moves from water to air is equal to BC over AC. Right? Now, look at this. This is as light moves from water to air. We want the absolute refractive index, not the reverse refractive index. So if the reverse refractive index is BC on AC, then the absolute refractive index as light moves from air to water, air, water, would be equal to the reverse of this. So AC over BC. Come back to this. What is AC? AC is from the object to the surface of the water. Audrey,
Sir, please, I'm lost.
where?
Sir, please, starting from refractive index of water to air.
So we are looking for the refractive index as light moves from water to air. And now it's telling us that refractive index is sine I over sine R. What we are doing is that we are considering small angle of incidence. And at small angle of incidence, sine I is equal to tan I. And then sine R is also equal to tan R. So all that we are doing is that this refractive index, we are expressing it in terms of tan I over tan R because they are equal. Now, we derive what tan I is. Tan I is C over AC. Then tan R, CD over BC. So times BC over CD. When you cancel out, you have BC over AC. But the refractive index as light moves from water, okay, light moves from water and coming out of air. But we are always looking for the real refractive index, absolute refractive index. And so instead of from water to air, we need from air to water. But that's the absolute expression. Meaning that the absolute refractive index as light moves from air to water would be equal to AC over BC. Okay, are you okay?
Yes, sir.
Then come back to the drawing. It's AC. AC is a real depth. Real depth. What is BC? BC is the apparent depth. And so whenever you place an object in water or under a glass prism, the refractive index of the denser object can be determined using the ratio of the real depth and apparent depth. All right. So all that we are saying is that for this optical illusion, refractive index can be calculated using real depth over apparent depth. So when an object is placed in liquid or is placed under glass prism, you can use this ratio to find the refractive index of the material by considering these two ratios of depth. Now look at what we have. AC is equal to real depth. CB or BC, apparent depth. But from what we have, we can say that CA or AC is equal to AB plus BC. So AC is equal to AB plus BC, where AC is a real depth, CB or BC is the apparent depth. So it means that AB, which is equal to AC minus BC, this measure AB is what we call as the displacement. The displacement, how the object is displaced. So when an object is placed in water, the vertical displacement is equal to the real depth minus the apparent depth. So the vertical displacement is when you have subtracted the apparent depth from the real depth. Okay. So this is the concept of real depth and apparent depth. We use this to find the refractive index of. So practically, when you drop a coin in water and you could measure the actual depth from the surface of the water to where the point is, and then you could measure the apparent position, height, apparent depth. You can use this information to calculate for the refractive index of the material. Let me connect an external speaker. All right. So that's it. Now let's look at total internal reflection. Total internal reflection. Even though we are doing refraction, but we are talking about reflection. So total internal reflection is reflection under refraction. Reflection and refraction of light. Total internal reflection. The question is, what is total internal reflection? Please, any idea? If you've read something around TIR, total internal reflection, please share it with us. Anybody? If you have an idea of what total internal reflection is. Okay. The concept of total internal reflection is very, very important. It is applied severally in engineering endeavors and in telecommunication. The telecoms use that to transmit information and voices, and it has a greater advantage over wires, copper wires used as conductors or used for transmitting information. So, what is total internal reflection? Now, whenever light total internal reflection, which is shortened as TIR. TIR. Now, whenever light, before I give you the definition, we have this as air, and then this is glass. Whenever light moves from a less dense medium into a dense medium, there's the normal. There's the incident ray. Once light is moving from less dense to a dense medium, it will deviate away from the normal. Now, whenever light travels incident on a medium, transparent medium, Part of the incident light, okay, because the glass is a transparent material. If it is water, water is also transparent. Okay.
Sir, please, you said when light moves from less dense to more dense, the light will deviate away from the normal.
Thank you. Thank you for the observation. It should be from denser medium to a less dense medium. So glass to air. Thank you. So when light travels from a more dense medium to a less dense medium, so from glass to air, the incident light, the refracted ray is bent away from the normal. Okay, but before then, whenever light hits a boundary, two things occur. Part of the incident light is refracted. So here, this becomes the refracted ray. And then part of it is reflected. Reflection also occurs. But what happens is that the reflected ray becomes so weak ray, whereas the refracted ray becomes stronger or brighter. This is because this is glass. Okay, the greater percentage of the incident light will be refracted, and a very small percentage will be reflected. This is the normal. Now, as we increase the angle of incidence in the denser medium, so as we increase this, maybe initially I is 15, we are increasing it progressively to 20, 25, 30. What happens is that as we increase the angle of incidence in the denser medium, the angle of refraction also increases. So you realize that as I increases, R also increases. Now, a certain value of I, or a particular value of I, value of I gives us an angle of refraction of 90 degrees. Gives an angle of refraction of 90 degrees. And this angle of incidence, which gives us an angle of refraction of 90, is special. Yeah, this is what I'm talking about. We are increasing I progressively. So there will be one particular angle of I where the angle of refraction, meaning the refracted ray, will just lie on the boundary between the two media. And when this happens, the angle of refraction here is 90 degrees. This angle of incidence, which gives us an angle of refraction of 90, is special. And so is given a particular name. And that is the angle, that particular angle of incidence which gives us an angle of refraction of 90, is known as the critical angle. The critical angle. So, what is the critical angle? The critical angle is the angle of incidence in a denser medium, that gives an angle of refraction of 90. The critical angle is the angle of incidence in the denser medium that produces an angle of refraction of 90 degrees. Class, are you there?
Yes, please.
So, because this angle is special, it is also given a special name known as the critical angle. The critical angle is therefore defined as the angle of incidence in a denser medium that produces an angle of refraction of 90 degrees in the less dense medium. Now, after attaining the critical angle, this is what happens. Any further increase, so if this is 90, then it means this angle is known as C, capital C, the critical angle. After obtaining the critical angle, any further increase in the angle of incidence, this is what happens. The moment you increase the angle beyond the critical angle a little, now all the refracted rays will be reflected. So this is what we'll have. When you go beyond the critical angle, we have the light, the incident light completely reflected. There wouldn't be refraction, but every incident light would be reflected. This is what we call as total internal reflection. Okay, this is what we call as total internal reflection. And quickly let's list the conditions for total internal reflection to occur. The conditions that must prevail for total internal reflection to occur. One, for TIR to occur, one, light, Leonard, light must travel from a dense medium or denser medium into a less dense medium. Other books, instead of less dense, they often use rare medium. So rare medium is a less dense medium. So for total internal reflection to occur, light must travel from a denser medium into a less dense medium. Then two, angle of incidence. Angle of incidence in the dense medium or denser medium must be equal to the critical angle. So the angle of incidence in the denser medium must be equal to the critical angle. And when these conditions prevail, every incident light will be totally or completely reflected. This is what we mean by total internal reflection. So I'll give you the definition in the next week, and then we go through the mathematics of total internal reflection. Please, any question? Hello, class. Any question?
No.
Okay. If there is no question, then this is where we draw the curtains on our meeting today. Thanks for everything. We'll continue next week. Have a very good or a very nice weekend. Bye bye.
Bye.